Hello, colleagues. It's my pleasure to welcome you to this supply response analysis using panel approach. The starting point is to set our working directory and import the data set. So we move to session. Let's set our working directory, choose directory. I'm using abil as my directory. Then the data set is cassava. So let me import the data sets. So this is my data set import. So let me return to the script file. Let's load the necessary packages. We need tidyverse to manipulate the data, panelr to show some charts. PLM is the main package for linear panel modeling. Then table 1 for some kind of descriptive statistics. Let's run this. Okay. So let's try to get some panel chart for the yield, area, and the price variables. The starting point is to define the structure of the panel. So we have panel underscore data. Cassava is our data set. State is the cross section, while the time dimension is year. Run. Having that, then we can plot the panel charts for yield. So we have line underscore plot yield. So here we are. We say the overlay should be false so that we have separate graph for different cross section. So we can repeat that also for the area as well as for the price. So we can, this is very simple and straightforward to explain. Next, we want to obtain the descriptive statistics of the variables necessary for our panel regression. To remind ourselves of the variables, we have spec cassava. Okay, let me use names. Names cassava. All right, so my column names include state ID, year, state, area, output, yield, price, year average for the temperature, then the growing degree days as GDD, then rain for the precipitation. In order to get the descriptive statistics, we need table 1. That is why we have table 1 package. So we have yield, area, output by various states. So we have the mean, the median, maximum, and maximum for all the variables. All we just need is to export this to Microsoft Word, which is pretty very straightforward to do. For our panel regression, we need 3 packages. We have the PLM, then LM test, and stargazer. So let's load the packages. Fine. Usually we want to start by running ordinary least square model, which is the simplest. So our yield is the dependent variable. Then we have price, growing degree days, rainfall as our variables. And theoretically, we bring in the climate variables in quadratic forms because it is expected that um, the climate variables will have a kind of L shape with the yield. So we run this and we may quickly check our results. So if you look at the results, the OLS show that the coefficient of price and rainfall are positive and statistically significant. And we can see that price, a unit increase in price will increase yield by about 0.005 tons per hectare. Having done that, we try to control for state effects. And to do that, we run a kind of fixed effect model. So we have the fixed effect models as within the effect as individual, that is the cross-section aspect of our data set, which is the states, the 6 states now. So let's run it and get the summary. We run this, so we get the summary here, sorry. The fixed effect model show that, let's look at it. You can see that even looking at the coefficient and magnitude of the coefficients, it's a bit better than the ordinary least square model. So the fixed effect model shows that price, growing degree day, are the basic drivers of the rising yield. But contrary to theoretical expectation, the growing degree day has U-shaped relationship with the yield instead of the expected L-shape. A unit increase in price will increase the yield by about 0.006 tons per hectare. It's slightly greater than that of ordinary least square. But before we conclude, there is a need to test for the state effect and compare excuse me, and compare the ordinary least square model with that of the fixed effect. So to do that, we have the PLM test for the fixed effect, where our effect now is the cross section. So we try to look at this. And if you look at the p-value, that's almost 0.000 something. So it suggests the presence of state effects. So we try to look at, to compare the fixed effect and the OLS by running the PF tests. And clearly, looking at the p-value, it shows that the fixed effect model is preferred to that of ordinary least square model. However, in addition to state fixed effect, there could be a number of factors affecting the yield that are not specific to the individual states. So we can model the time fixed effects using the effect time equals to time argument in our PLM model. So let's try to consider the time effects. So this is what we are trying to do here. We call that one T. So we run this. So let's get the summary. So this is, here we are, the summary of the results. So, and let's look at it. If you carefully look at it now, the coefficient of price variable is the only meaningful variable in the time effect model, and it's negative, contrary to theoretical expectation. So let us run the PLM test on the time effect model to verify if the time fixed effects are indeed present in the model. So we try to do this just as we did for the individual fixed effect. So we run this. And if you look at it, the p-value is 0.99, so which is clearly indicating that there is no time fixed effect. So we try to present the three models we have done in just one table. And this is what we're using the stargazer package to do. So we have wireless FET, then we name the output as reg.htm. So we run this. So and we get your results. If you go to the to your directory, definitely it's there. The only thing is that you right click and you open it as Microsoft Word. For the panel data, we need to address the potential for serial correlation in the error term. So we use a Branch-Godfrey test. So this is what we are trying to do here. Since our focus now is the fixed effect model, so we run it, and you can see the p-value is quite very small. So this is confirming the presence of serial correlation, and which we need to correct that. So we correct that by running the coefficient test. So our coefficient test is what I'm trying to run here. So I try to do this so that we can actually get a better standard error than what we have for the fixed effect. So this is what we have done here, and I try to compare the fixed effect with this coefficient test model. So, and I export it to Microsoft Word so we can get it in our directory. So after correcting for the serial correlation, if you look at the results, only price, and we see that price is no longer significant. What is left is just the climate variables. But let us think that if the government should introduce a new species of cassava, we know that the change will definitely affect all the 36 states. And this is a typical example of cross-sectional dependence. And the fixed effects model does not capture this. Another example, which is ongoing in Nigeria, is the effect of the bandits. Let's take, for instance, that the bandits stop cassava farmers in the country for farming. It's going to have a nationwide effect on the yield of cassava. So we try to test for cross-sectional dependence. This is what we are trying to do here for the fixed effect model. So we look at it. Fine, now we have 0.573 as our p-value, which is clearly showing that there is no cross-sectional dependence. So now that we have carried out necessary diagnostic, sorry, spelling error, diagnostic test, then we can report with some confidence some of our results, and which means we have to base all our recommendation on the fixed effect model. So the final regression table, as we have the OLS, the fixed effects. This is our coefficient test for the fixed effects. This is time effect model. So these are all what we've done. So, and I name it panel regression. So we run this. Yeah, so we can actually go to, so let me show us the results. So let me minimize this. panel, panelr, panelr. Okay, this is it here. So I right click here. This is what I'm saying. So open with Microsoft Word. So here is the final results. So, and the one that you have to discuss is this coefficient test. So, and we know that the only meaningful variable is the growing degree days. So, and that is where we have to lay the emphasis. And this is clearly showing that um, climate change actually um, does not affect cassava negatively as far as Nigeria is concerned, because a unit increase in growing degree days actually increase the yield of cassava. So thank you. I think the conclusion is very, very straightforward. And another meaningful thing from the analysis is the fact that it is just not enough to look at supply response as a function of price alone. So it is always good to cater for the climate change effects. So thank you.